Hello, thank you for coming out today. Looks like a good crowd. I hope you are able to vote, have voted today. Important thing, so I want to plug for that. I'm really pleased I'm Alan McMillan, by the way. I'm pleased to introduce my colleague and collaborator, Jameson Merkow. He was actually born and raised here in Madison till he was a teenager. He went to Tulane University for his undergraduate in computer engineering. Got a master's degree in AI at Carnegie Mellon, and then a PhD in AI and medical imaging at University of California, San Diego. CTO at a startup for 5 years prior to joining Microsoft about 4 years. And we've been collaborating in some of the areas that we'll talk about today. And we're really happy to have Microsoft here on campus. There's some events happening over at school, learning more about how to use tools, connecting with Azure. But today, Jameson's going to talk about foundation models and how we're using them for research.
Thank you. So as Alan mentioned, I'm from Microsoft, and Microsoft's mission is to empower every person on the planet or in every organization to achieve more. But what does that really mean for healthcare? And so in the era of AI, Microsoft has one of the best. Well, I guess first of all, this isn't like a sales thing all the time. I'm just setting it up. So we'll get to the more interesting stuff in a second. But so Microsoft has a suite of tools that include Nuance, which is our vertical solutions for that enable various clinical and research outcomes. We have Microsoft Fabric, which is an end-to-end analytics tool that you can unify your data within that. You can connect to LLMs and LFMs. It has connectivity to Microsoft Suite and lots of different partner products. We also have Microsoft Copilot, which you are probably familiar with maybe GitHub Copilot. But if you're using Teams, there's a version of it in Teams that's on Bing, it's in Edge. Pretty much any Microsoft product these days has some sort of Copilot within it. And of course, there's Azure, which is Microsoft's cloud offering. And so the Azure includes purpose-built AI tools and compute infrastructure, so you can do essentially whatever you want in healthcare or any other application. And so what does that actually mean for healthcare? So Microsoft is the only cloud provider that has a suite of tools that manages everything from discovery through development and delivery of AI tools. And our team specifically deals with these healthcare or health and life sciences AI models. I work in health and life sciences department at Microsoft. And so these are the models and things that I'm going to discuss today. So we're on the precipice of an incredible opportunity. We have incredible amounts of compute. We have huge amounts of siloed data. And in healthcare, 99% of that data is in text. And so we do have all these existing large language models, GPT, DeepSeek, et cetera, but they're not great at understanding medical descriptions, particularly medical imaging. And so how do we get from where we're at with these tools like GPT or O1 or DeepSeek into a fully integrated tool for healthcare? And so the Microsoft's answer to that is to use multimodal healthcare foundation models through their multimodal healthcare AI platform and AI Foundry and Azure ML. So this is essentially a curated set of tools that you can use today. If you have an Azure account, you can connect and just try out all these different models. They're easy to deploy. You can try them out on your own data. You can try them out on experimental data. And they're also all open source. So you can download them, try them on your own metal, fine tune them, etc. And and go on from there. And so this is the roughly the suite of models that we're looking at. So we have essentially three sections: the embeddings, which include Microsoft MetaImage Insight, Page, Virchow, Province, GigaPath. And these produce, if you're not familiar with embedding models, they take input and produce a vector string that's a consistent length, so you can use it in various other tools. We also have segmentation. The two offerings here are the MetaImage Parse and NVIDIA's Vista 3D. And then we do also have image-to-text foundation models, which include the Microsoft CXR Report Gen and Page Prism. And today I'm going to concentrate mostly on the Microsoft offerings, starting with Microsoft's MetaImage Insight. And this is an open source, state-of-the-art embedding model that's been trained across 9 different medical imaging modalities. And it achieves state-of-the-art performance essentially across the board on downstream tasks using the embedding model. Now, I'll go into a bunch of different examples of different use cases and different things that you can use it for beyond what you're seeing here in this graph, or in this slide. Next is the MetaImage Parse, which is a kind of like a segment anything model. And it uses image embeddings and an adapter to generate text, to generate segmentation masks based on text inputs. And so as you can see in this GIF, you can put in, different types of text prompts, and it'll output a segmentation mask for those. And it also works across lots of different modalities: dermatology, OCT, ultrasound, the MR and CT, mammogram, X-ray, and even pathology. Lastly is Microsoft's CXR Report Gen. And so this is an open tool, image to findings generation tool. So essentially you put in an image, or really it's actually a set of images, and it'll generate a list of findings. So if you look at a radiology report, this would be the findings section of that report, as well as the bounding boxes of where those things are located within the image. So this allows you to generate grounded findings using the AI. So you can actually look at, why did this say it had what's on here, cardiac size marginally enlarged? What's the evidence in the image for that? And you can highlight it within the image. So also, if you have any questions, please just stop. It's not, you raise your hand or anything. I'll slow down. But so what can we do with these models? So we can start by, one of the most popular things that we're using is the embedding model. The embedding model can be used for things like quality control, image search, and out of the box, it can facilitate a number of different types of applications. And I'll talk a little bit about the specifics of those. You can also train an adapter on top of this model to build whatever you want. And this is essentially how MetaImage Parse works. And so you can use it to create a segmentation model, where it's simply you can use it to create a classification model based on your siloed data that's perhaps you have already embedded number of images. You can train a classifier in 30 seconds rather than a week. And so it's extremely, the embedding model is extremely versatile. You can also fine-tune this model for specific tasks. So if you have say you have a 10th modality, say GI, that's not covered in by MetaImage Insight or one of our models, you can also fine-tune these to work better on that data, or work better specifically on your data. Say you have different types of scanners, or you're not seeing the performance you like, you can fine-tune the actual embedding model to work specifically to your type of data. And so the idea at Microsoft to sort of unify all these things into the overall model is to use them with LLMs. So the pilot program, or the pilot example of this, is the CXR report gen. And this is what you were seeing there is roughly the architecture of it. It has multiple images and text prompts, but essentially it's a text embedder with a task adapter and then with a LLM on top, all trained to generate findings based on the multiple images as input. So if we take this idea and we want to build a comprehensive tool, AI, for multiple modalities, Microsoft's position or strategy here is to not try to train O1 or DeepSeek to fine tune it for radiology, molecular medicine, all of these different categories, but instead use foundation models that have been trained on those specific modalities to provide information to that LLM, and then allow the LLMs to do all the reasoning. So what we're finding is that it's actually really difficult to fine tune or to train the large scale LLMs like GPT, O1, et cetera, on new data. And we, generally speaking, don't actually see a very large performance boost from trying to retrain O1, for example. And oftentimes the performance actually goes down. And so what we're doing instead is to generate findings or generate inputs from foundation models that inform the LLM models on what's important about those images. And so the advantage of this is multifaceted, in that, so every couple months there's a new model, right? So I think 3 weeks ago, 4.5 came out. Before that, it was DeepSeek. Before that, it was O3. Before that, it was O1. And so there's a new model every so often, almost every month now that's coming out. And if you're trying to fine tune those over and over again, you're never really going to end that cycle. And so by doing this, you're allowing the performance of your fine-tuned models of your foundation models to transfer to the LLM, and you can swap that out for the latest and greatest AI reasoner and continue your tasks. It also allows for much better grounding. So if you're observing what the foundation models are doing, you can get direct evidence of why it's making those calls, just like with CXR Report Chat. And so I'm going to go through a bunch of different use cases that we've developed for using these foundation models. The first four, classification, exam parameter detection, outlier, and multimodal analysis, I'm just going to talk a little bit about for the sake of time. And then if there's interest in some of those and we have time at the end, I can jump into more details. But I'll have a little bit longer discussion about pixel search or image search, monitoring, model monitoring, data monitoring, image to findings, which is CXR report gen, agents. So I have an actual example of how we're using these foundation models in a multi-agent system. And then finally, example of fine tuning, which is now available natively on Azure as well. So first, it's classification. So as I mentioned earlier, you can very quickly and easily turn these embeddings into a powerful classifier with fairly minimal effort. And so there's practical advantages to this. So you don't have to use a lot more annotations. You can do it on a smaller sample of images, 100,000 that scale, rather than millions of images for trying to retrain DenseNet or some of these larger models. It's pretty easy to implement. You don't even necessarily need to use like a PyTorch or one of those. You can use scikit-learn and just throw the embeddings as if it's a tabular data. And it's also, you can try multiple approaches. So you could do zero-shot learning, and I'll show an example of I have some. The zero-shot learning is basically, since MetaImage Insight is both an image and text embedder, you can take the image embedding and compare it to text embedding, essentially your labels, and then generate a new classifier based on that. You can also use just the image embedding side and use few shot learning in like a KNN style, uh, nearest neighbor model. You can also train different types of adapters for specific tasks that can include MLPs, Mambas, or any type of model. Yeah.
Just very quickly, what is MI2?
Oh, sorry. Image Insight. So that I should have expanded that. So Image Insight is a mouthful, so we start shortening it to MI2. And so there's not a MI1. It's just two I's. So instead of me, it'd be say MI2. That makes sense. Any other questions? All right, so here's some of the architectures that I was just talking about. So the top is a zero-shot learning module. And so as I mentioned, MI2 MetaImage Insight is both it's both an image and text embedder. And so this example has the text embeddings pre-computed for you, but you put in a new image through the system, you calculate its image embedding, and you compare it to the text embeddings of the same model. And so the goal of MI2 is to essentially take image and text and putting them in the same embedding space. And so by doing this, you can essentially put your labels in as text embeddings and then find their similarity to the image embedding. And that it actually produces a pretty powerful classifier. You can also do a KNN style where you basically you think of it as SVD or PCA, and you essentially use the embeddings to encode the images, and then you can calculate the distance to specific clusters of images. Lastly, there's an adapter. So you can directly train, for example, an MLP adapter based on the embeddings to essentially creating a new classifier. And not only is this useful for creating just a classifier, we also find that it's useful for in lots of different applications like image search or other things where you want the image search you want certain elements of the images to surface through the embedding. So if you have a database of, say, the tumor sizes, you can have embeddings based on adapted embeddings based on that, and now when you do image search, you'll find cases that have similar sizes and numbers of tumors within them. And so this is actually a result that she's back there. Sorry to put you on the spot. That came up with that compared MetaImage Insight to a bunch of different models using essentially different hats on top of the embedding model. And so like KNN, logistic regression, SVM, random forest, or MLP. And so all they're doing is taking the image embedding and outputting and creating a classifier on that and then testing it. And when comparing to these other models, MetaImage Insight turns out to be the best. It kind of blows them all out of the water. And even to the point where we tried to mix the MetaImage Insight with results or with embeddings from other models, and that actually decreased results. So it's an extremely powerful embedding tool that has a lot of descriptive power. So next is exam parameter detection. So this is an actual application that we're working on right now with a major vendor for how to essentially as images come in, you need to classify them as different modality types. And this is a problem that arises in like viewers and things like that, where the DICOM metadata isn't sufficient to really tell you exactly what that image is, or there's errors in it, missing values, or there's 150 different strings for the same thing. And so they need to narrow down, particularly for like routing through a vendor system or things like hanging protocols and all of that. And so you can do this with minimal effort. And And it's actually, this is being worked on right now to be integrated in products using MetaImage Insight. And so here's, see, it's going to start. So here's an example of how you can use adapters to have different types of embedding surface through the through MetaImage Insight. So there's essentially adapters that are trained to recognize different types of anatomy, different types of image sequences and contrasts. And you can see that this is a UMAP projection of those of the resulting embeddings, and you can see that they cluster in various different in ways that are aligned with their anatomy, image sequence, or contrast, all based on the same image embeddings. Another example is outlier detection. And so as you can imagine, as I mentioned earlier, there's lots of different use cases that you can use it for, and QC is one of them. And so one of the things that we've also been working on is using the outlier detection, not just to filter out individual images, but you can also use it on full 3D volumes or even entire studies. And so what we've been using it for is clinical trials. So essentially they have, in clinical trials, they have very strict protocols of what is accepted and what's not. And so for this, the particular one that we tested it on, they had strict protocols for CT abdomen pelvis, and they had to have very specific landmarks on the top and bottom. If those weren't in view, they would need to throw that out. And so the current way of doing that was someone would have to look at the first and the last one of all of these volumes to make sure that it was included. Then I had to go through and make sure there weren't any other artifacts, metal, or other things that motion within those images. And as you can imagine, incredibly slow. So what we did is we used MetaImage Insight to generate a reference set based on ones that they knew were powerful or knew were good. We used MetaImage Insight to create a vector image vectorization, and then we did per study and distribution analysis, something very simple that's just essentially computing statistics across the study. And then from there, we can develop a reference distribution for either one or many reference distribution. And then when a new study comes in, you do the same process of embedding it and then calculating the distribution. And then you can use that with a Canon classifier or all of the other methods I've already described with, create a new adapter on it, or Canon. I guess the image to text, the text to embedding won't work, but all these other methods will be effective. And so what we found, what we tested it on, was the way we actually ended up testing it is to take the top, essentially just take the reference set, take the top image or the bottom image off, and see if the system could detect it, and ended up catching all of them but one or two of these outliers, and detecting them as outliers. And that was with no training, just using statistical analysis. One of the other use cases this is a paper that's being submitted to Mackay right now, and there's a white paper out on it, is combining multiple images into, not only multiple images into a new embedding, but also combining multiple modalities into a new embedding to generate a classifier. So what this is doing is accepting MR images that are tied to histopath images of the same patient to generate a prediction of the survival outcomes. So those are it's essentially a regression problem. And so they tell you more or less how long someone has to live based on these adapters. And we're seeing extremely powerful results from this. And this is actually using two different foundation models that we're providing. The first is MetaImage Insight, and the other is GigaPath, which is provided from Providence. All right, so those are the short versions. Um, and we'll get into the longer discussion setting image search. Before I move on, are there any questions on those? Is everyone? Yeah.
For that multimodal example, could you just say a little bit about how you built that foundational model so that from taking data from different hospitals and out to
The page or Management Insight. So not page, it's Providence. So they built that's actually something else that is allowed, or I guess another feature of the catalog where we have all these models that are open source is that other people can add. And so this model is actually built by Providence. So I'm not sure the exact training procedure. A lot of it is we have like a model card, so I can follow up with you and give you that as much information as available for that.
I guess my follow up is how can we trust the model? Do we think it's accurate enough, or
so that's a great question. So that's on you, I guess. So that we're not trying to present these as you throw this out and now you're ready to go to the clinic, but Microsoft's not really interested in competing with other companies on building their classifier. What we want to do is help you build your own classifiers that you can use very quickly and easily. And so if you try this and you have a certain score in mind, you'll have to look at empirically what score you get on your data set. So you'll have to do your own analysis of the results. But
all are able to find tune?
Yes. So some of them you're able to do it very easily right now, particularly Management Insight, and that's one of the slides one of the things I'll go over. And some of them that are from vendors or from other places aren't. So the three main ones, Management Insight, you can fine tune now. Like it's not a button click, it's a notebook, like a Python notebook that you can run through. Eventually it'll be a button click, but it's in public preview mode right now, which basically means it works, but doesn't have very good features yet. And then MetaImage Parse, you can also fine tune. It's it's a separate process, but we're working on moving all of that into like the same area. And then CXR Report Gen, we're working on it right now to release code to be able to fine tune it. Yeah. So, but in the meantime, you can also build these adapters, which get you a lot of the way, but they don't get you all the way for everything. So, yeah. I think you had a question too.
So first off, whenever we're doing this, is there a big difference in performance between fine tuning and not fine tuning MI2? And then secondly is, where are you getting the data to train all of these on your end?
So most of MI2, so that's a great question, especially about where the data is coming from. So these are all built using data that can be commercialized. So for a lot of these models, there's for example, CXR Report Gen is a different version of MIRA2, which is a model that came out, I think, 2 years ago. And essentially the main difference is CXR Report Gen is trained using data that the model can be commercialized or it can be used for anything. So the vast majority of the data is used for open source from open source projects. I think both, I'll have to double check, but I think MI2, MetaImage Parse, and CXR Report Gen are all trained exclusively on open source data that allows the result to be commercialized as well. But that information is also, I'll maybe at the end I can connect the model card and answer a little bit both your questions, because we have a lot of this information saved with the model. It's like a README that tells you exactly the performance and lots of different applications, tells you specifically what data was trained on, and gives you lots of other little tidbits of good best practices to how to use it.
So then, as a quick follow-up, is there any guarantee that when I take my data and fine-tune it with this, that it doesn't get leaked through to the model so that someone else knows?
Yeah, that's also a great question. So these models, if you deploy them, they deploy in your tenant, and we have zero access. Microsoft can't get to them ever. And so if you're fine-tuning them or you're using them, we never get access to that data at all. I mean, it's impossible, like to the point where if something breaks and you have to give us access to try to help you if you want us to do that, which we do, doesn't actually come up that often. But yeah, all of your data is yours. You can use these all the time. It's not like, so if you wanted to use like OpenAI models, Azure has their own OpenAI versions of those. And the main difference is when you use OpenAI directly, they have rights to the data. So if you go to, ChatGPT, they can, whatever you submit, they can use for training. That's part of the end user agreement. With Microsoft's models, that's not the case. They don't store any of your data.
Like you store the weights, like say that a combined data model, reasonably the weights could recover some of the data or some elements of the data.
You store the weights in your tenant. So if you fine tune it, it gets stored with you. So it's like in the same secure location that you would put PHI or whatever. It's all stored with your. We don't take it. So all the mechanisms that Microsoft uses to deploy models, create endpoints, all of that we use exactly the same that you would use. And so the nice thing about that is that when you deploy one of the models that's hosted in the catalog, it gets deployed into your tenant. And then if you fine tune a model, you can very easily just redeploy that model in your tenant, just like you would almost exactly the same way. And that includes, and you can also use it to fine tune again. So you could fine tune a model and then fine tune it again, but in the same, like basically switching out a string that identifies it. Yeah.
It's one of those guys, aside from healthcare applications at the clinical side, say if you fine tune an image technology search model for, say, instead of very specific disease classifiers that are not common. So you want to publish that. What are of that?
So you want to publish it so other people that are outside your organization can use it. So within your organization, it's really easy, and you put this model registry, and you can share that with your entire tenant to get them on the model catalog, so anybody can use them. It's a little bit more difficult. It's a human. You have to go through people, but there are pathways that you can take to do that. So that's how we've gotten all models. Yeah.
All of that is
So as long as all the essentially there's a lot more paperwork to get it because you have to figure out the licensing, all of that stuff. So it's a little bit longer process, not something that's automatic, but if we can follow up afterwards. I can connect you with the person who does that. This will through our team. And so we can, if that's something that's interesting. And not only that, is they're working on monetization. So if you train a model and you want to put it in the model catalog this very soon, might even be available right now, you can monetize that. And so when someone uses it, you can get a chunk of, get some kickback from it. So image search. So I'm not sure if people here are familiar with image search in general as a concept, but you've probably seen it on, Google has an image search, Bing has an image search where you put an image in and it finds images that are similar. And so the same concept can be applied to medical images. And so this can help you find cases or exams that have very similar features, very similar pathologies, et cetera, when you're examining a patient. And so one of the best reasons to do this is that it can support your evidence-based cohort diagnostics. And so you can get more accurate predictions based on that, and you can look at the different treatment options of similar patients. It can also be used as a teaching index. So if you're wanting to find other images that are similar to explain a particular image, you can also use it in that way. And so there's a lot of potential for these systems for enhancing healthcare as well as medical education. And so the MetaImage, this is specifically using MetaImage Insight, but it can also be applied to other embedding models. But there's lots of different types of image search that you can do. And so we have we have a repository of examples that I'll share at the end as well. We have a lot of those already in there. So image to image. So if you put a 2D image in, you can find similar 2D images. You can do volume to volume. So volume goes in, you find similar volumes. Text to image. So you write a caption and you find images that might match that caption. Same thing with image to text. You have a image and you want to find text that's similar within your database. And then also this last one isn't in the database in the code yet, but it's coming out in the next couple of weeks, is cross-modality image search. So you can, based on input image, you can find the cases or the exams of the cross-modality. So you could put in, say, an MR image and find the histopathologies that are the closest to it. And so this 3D image search is actually a pretty difficult problem, and it hasn't been tackled too much. And so there wasn't a benchmark involved with this yet. So we ended up creating one. And this benchmark is based on similar lesion counts. And well, it's based on a couple of different descriptors. So the number of lesions within the image, the morphology, so the size and the shape of it, and also the where it is in the image along with the size and the shape. So like a liver, 1 millimeter, I don't know the different shape codes, but so that type of thing. And so you can, we built a benchmark for this that we could test against. And so the overall process is, I guess, there's multiple stages. So you create a data set or a reference data set of encoded volumetric embeddings. Then you store those in a database, and then those are indexed to the information of where they came from. And so then in your sort of test mode, you take in a test test image, and optionally along with the captions of what type of similarities that you are looking at, and you embed all of it together to search through the memory bank that you created on the first step. And then that allows you to do some the retrieval. So, search. And so there's also a couple of different methods of doing that. So there's like the zero shot methods. So those take volume as a set of slices as a query. So this is very similar to the outlier detection, but in this case, in the first one, it's looking at slice by slice how many matches you get per volume, and then based on that, you have you can match, and so it's kind of like voting. So, which you should do today, by the way, too. But so if a volume has 15 matches, another one has 12, the 15 would be higher ranked in the aggregation. So also where you combine the slices exactly like in the outlier detection, which is essentially here using some sort of aggregation. So that mean, median, max, pooling, those types of things across the image vectors. And that generates a new index based on the entire volume, and now you can use that to do your search. And so then the last one is about adapter based, and so this is the more multimodal version of this, where the image or volume goes into the image encoder, and then you can use GPT. In this case, we use GPT-4 to build the description of the image, so a text description, and then we encode that description And so we end up with 2 embeddings and use a multimodal adapter to generate a new set of embeddings that we can use for search. And so this is evaluated against the benchmark that we generated, and it got extremely promising results. And this is being published in Mackay, I think, it's under review right now. So next is image findings. And so this is just an example of how you can actually use this model right now. So this is in AI Foundry, which is the sort of the no-code version of Azure ML. And so this is actually going through an example of using it. And you can deploy a playground within, if you're at the morning session on the other side of town, we were talking a lot about AI Foundry. And so you can create one of those playgrounds that we were looking at. And so it's select CXR report gen, and this is a screenshot of the actual card. And so this is where a lot of the information that you guys were looking at is. So like it shows you the architecture, tells you some of the more information, and if you scroll on it, it'll also compare it to other types of models, etc. You click deploy, and this will deploy. Like it's that easy to deploy a model, and you can go ahead and use it in a playground. And so once it's in the playground, you can actually connect it to your prompt. So this is a good way to evaluate it in an interactive way, not necessarily an evaluation of 10,000 images, but if you just want to try it out and see how it works, this is a great way to do it. So you put in your indication, and you drop the images in, and then based on those images, it'll analyze your image and then generate your findings. And so when you hover over these different findings, it'll automatically highlight the region within the image that is that it found the reason it had that finding.
James, you can attach PDF, PNG, and then
I think right now it supports PNG only. I'll have to check. It might support DICOM as well. I'll have to check. Yeah. So the next is drift monitoring. So this is a longer, a bigger use case, more involved. But so I'm gonna set it up a little bit. So say you've deployed a model, right? And on day 0, you run some sort of test, and that test tells you maybe the AUROC of that X-ray model. And so after that point, this model's in production, it's running on live data, but how do you actually see what the performance is? So say you did another test, like an audit on day 95. So you don't really actually know what happened between those 2 days. Right. So the performance could have kind of dipped for a little bit and then goes back up. It could be part of a trend that where, so there's some big drift event and now the performance is going to be really low. Maybe it's sort of random and it's just not very consistent. So how do you know what's actually doing? And so this is a paper that we're right now. It's available on arXiv. It's under review at Nature Biomedical Engineering, and essentially what we're doing is being able to try to answer some of these questions without actually having to do ground truth, having to use ground truth. So it starts with a raw data stream, and you use MetaImage Insight to embed all of those images, the images in your data stream. You can also use extract the metadata directly from either the EHR or the DICOM image. So things like all the patient details, demographics, the imaging, like image capture details, and then also you can capture the model predictions from your AI classifier. And this essentially creates a new embedding overall. So I'm kind of abusing embedding here a little bit. So the second thing is more of like a transform into a new space that's it's a multimodal space of image embedding, text results, or in demographics, so age, that type of thing, but also the categorical, so what type of manufacturer or model the image did the imaging. And so to do drift monitoring, you first select a reference set. So typically this is something that you already know ground truth for, and you have known performance statistics on. And then you have a detection window, which is, say, the last 2 weeks of data on your deployment. And you compare those metrics individually using statistical tests. In this case, we're using we use Earth mover's distance, and I forgot the second one, but we're using a categorical and a real value test to see to generate similarity between those two data sets. And so this gives you a score for each feature. So age would have a drift metric. The overall image embedding would have a drift metric. For Earth mover's distance is multi-dimensional. And then what you end up with is a bunch of different metrics, but you don't know which ones are important. You don't know if that's a normal fluctuation. So say in your reference set, the average age was 58, but maybe when you look closer, you can see that it actually changes between 58 or like 56 and 60. And so what's like a normal fluctuation of age throughout your data set? And so we normalize based on that calculation, and then we weigh them based on whatever is important to you. In this case, we're using the performance metrics. So which ones correlate with poor performance or good performance or changes in performance. And we merge those together, and what we end up with is we merge them through simple aggregation. We end up with what we call MMC, which is multimodal concordance, which is essentially asking how similar is this data to the reference set where you know that it has known performance. And the cool thing about this is that since we did this merging at the end, you can go backwards. So you can say, oh, we're under drift. Everything's, the MMC is really, really high. There's a lot of drift going on. Why is that? And so you can drill down and say, oh, the age has shifted, or the images are looking really different, or the predictions are way, the distribution of predictions are way off. And so you can sort of actually drill down into the reasons behind that. And so we tested this on a data set collected from MGB. That included COVID. So it's about a year before and a year after COVID occurred. And so we essentially simulated creating a classifier and deploying it before COVID. And then we wanted to see how the model would detect drift in that scenario. And what we found was really interesting. We're actually able to drill down enough to actually piece together entire narratives. And so what happened was there was no policy changes or anything like that. The radiology techs just didn't want to get into elevators with patients who were potentially COVID positive. So back then, people were extremely fearful of catching COVID, and there's a lot of hysteria around it. So they wouldn't, they didn't want to get in an elevator with them because of enclosed space. So they started going to these portable machines on the same floor. And so we saw a lot of drift in the different, essentially the model and manufacturer of the machines used. And then at the second dip, they started using it again. They're getting in the elevator again more. But then they also ordered a whole bunch of new portable machines and had machines moved from the vendor. But when the vendor came, the vendor set up the new machines, not the hospital, like they did with the ones they already had. And now these new machines are set up in a completely different way. And so they had the wrong monochrome, the wrong bit bit rate, and all of these settings are completely different. And you can imagine how that might affect AI classifier, depending on how, how it's tuned to your particular data. And so what we discovered was it's not necessarily a prediction of when you're going to have bad performance, but instead you kind of reverse it. So it's a great predictor of if your performance is very likely to be fine. So we think of it as like a check engine light. So if your performance is above a certain value, you should do an audit. You should look into it, and you can even go backwards in that original scenario where you do a quarterly audit. You can start to see where your changes occur. So we'll I'll go through agents a little bit. I'll kind of rush through or short on time, but so I don't know if people are familiar with multi-agent frameworks or multi-agent systems, but essentially what the way they work is that you interact with a number of different agents that all have different responsibilities, and those agents are able to make function calls to tools. So you can think of it like they're able to call a Python function, and then those tools are connected to some sort of backend. So that backend, for example, like RAG is a database. So for a RAG, this would look like a database search that's connected to your document files. But you could also connect this to anything. So what we've done is connect them to MetaImage Insight, connect them to DXR Report Gen as a back end. And this is sort of the end goal that we're showing earlier of having an LLM on top and then having the tools come to that LLM. And so we have, this is sort of a demo version of it that more like a proof of concept. This is like the architecture. So you can see we have some of these agents that are connected to like a RIS or a database type of application. It's all the data is fake, so it doesn't really matter. But we have then we have radiologist agent that produces initial list of findings, and then we can compare the radiologist findings to findings from various different other agents. So like the image search tool, we can see what types of pathologies similar images had. The image description agent is essentially a zero-shot classifier based on MetaImage Insight. And then we also use zero-shot for image type tool, which is essentially within this system, we need to route the images correctly. So you put in a frontal and a lateral, the agents need to know what type of image they are so they can properly assign them. I can show this video. It's all right. So I'll just explain. So essentially we have, this is a demo. So essentially we have a couple of different models here, a couple of different demos that you can select. And so part of what happens in the demo is that it's going to take the first three images. The first two are correct images that should be input, and then the last one is something that's completely irrelevant. So say you accidentally added the wrong image, but it's just to show how it can analyze these images and disregard them. And then the prompt below that says like, here's the patient ID. This is the indication is a pneumonia follow-up, and you're not sure if it's a comparison. You don't know if this has a previous exam to look at, and so you want the agent to find that previous exam. And so the agents start by essentially generating a orchestrated list of steps to perform these tasks for you. So for example, we need to parse out what's going on with the prompt and then make sure, like, is this a comparison? Is this not? Like, is there any extra information in there that I should be aware of? I need to look up the patient history and see if there's any relevant details there. So, maybe they have a, chronic condition, or, in this example, there's a comparison that is required. We have an exam parameter agent that uses the same technology as, that I was showing earlier to examine the parameters of both the image and the metadata to see what type of image they are. In this case, you need to know if it's frontal, lateral, or if it's just irrelevant. You have radiologists, which is DXR Report Gen, And then we have the med text description agent, which is zero shot, an image search. And then finally we have an agent that analyzes all of this and tells us like what's important, what's not, based on all this information. And then this is all passed to a writer, a report writer that understands how to actually write reports. So I'm gonna jump around. Well, so I think we're short on time, so we're pretty much at the end. So there's a bunch of sessions later. I'm happy to show you this demo. I can even actually run it for you if you want. And so I guess I'll just end with, we also, as I mentioned, we were able to fine tune. So this is something you can do right now. It's available tomorrow in the afternoon. We'll go over sort of everything that you've seen, all of these use cases. We have a code repository with examples of them, and you can try them yourself and then extend them to your own code or your own data. That includes fine tuning, and yeah, I think so. I think that's it. So here, there's a QR code for the examples database if you can't make it tomorrow, but we'll go through them. They're all based on Azure, so hopefully, if you need help on learning how to use Azure ML, happy to have you tomorrow. And thank you.